Okay, so here we have this cantilever beam, and we'll start out with marking the support as point A, as well as the positive and negative directions for our X and Y axes. Thirdly, let's mark our unknown reaction forces, which is one horizontal reaction force, one vertical reaction force, and one reaction moment. The horizontal reaction force Fxa will be equal to 0 because we have no other horizontal forces reacting on this beam. The second unknown is Fya, and the third unknown is the reaction moment Ma. And we'll start with calculating the reaction force Fya. We'll use the sum of forces in the y direction, or in other words, in the vertical direction. And this has to be equal to 0, because otherwise if the sum of forces in the y direction would not be equal to 0, this beam would be moving in the vertical direction. And in a stable structure, we don't want that. So let's just add up all the vertical forces. The first one being our unknown Fya. Second one is the distributed load 7, and since we have it for 3 meters, it is 7 times 3. Third one being the final concentrated load, 23 kilonewtons, and this sum is equal to 0. Now let's use our calculator to find out that Fya is equal to 44 kilonewtons. Now let's use the sum of moments to calculate our unknown reaction moment. And the sum of moments again has to be equal to 0. And we'll find these moments relative at point A. And this has to be equal to 0. If it were not to be equal to 0, if the sum of moments were not to be equal to 0, then this beam would just rotate around, and we don't want that. So the first force that will create a moment is this distributed load, 7 kilonewtons, and we have to make it to a concentrated load. So we multiply it by 3 of how much we have this load, and we will multiply that with its moment arm, which is 4.5. Next up we have a moment which is acting clockwise, and we have marked our moments as clockwise will be positive moments, so this will be plus 12 kilonewton meters. Thirdly, we will have this third load, which is 23 kilonewtons times its moment arm, which is 8 meters. And finally, we will write our unknown, which will be a negative moment, because we have drawn it as counterclockwise. And yeah, this has to be equal to 0. Now the reason we didn't add force Fxa or force Fya to this equation is because their moment arms are equal to 0. So theoretically we can add those forces, but then we have to just multiply these forces by 0, and for sake of convenience I just decided to leave them out. Now let's use our calculator to find out how much is this moment, and we will get that this moment is equal to 290.5 kilonewton meters. Now let's move on to drawing our shear force diagram. Just a reminder that the shear force diagram will show what is going on inside the beam. We have marked our vertical direction to be positive when forces go down. So when we have a reaction force, first of all we have a reaction force Fya that is going up, then it will create an opposite shearing within the beam that has the same magnitude. So the first force Fya is a negative force, but it creates an opposite shearing, which is a positive shearing. So the first force will create shearing of 44 kilonewtons. Next up, we have this distributed load, which will be in this graphed as a linear line, because after every very short amount of distance there will be a loading. And again, since this load is a negative force, it will create a positive shearing within the beam. And then we will have nothing until the final force of 23 kilonewtons. And we can also point out that 7 times 3, 44 minus 7 times 3 is equal to 23, and 23 kilonewton force right at the end of the beam is a negative force, is a positive force, which will create again negative shearing. So 23 minus 23 will give us 0. One question that you may also have is, why didn't we add the moments? Because the moments create normal forces within the beam, but in shear force diagram the only thing we care about is shearing forces. So let's move on to the moment diagram. Again, in moment diagram we are looking what is going on inside the beam as far as moments go, and moments create normal forces, and we draw our moments diagram to the side that is stretched out, and we will use the method of integrating the shear force diagram. Therefore, firstly we have this reaction moment, which is equal to 290.5 kilonewton meters, and right after that we have this square that has a height. In the shear force diagram we have this square which has a height of 44 kilonewtons and a base of 3 meters, and this will give us 132 kilonewton meter moment. So firstly the graph will go up because this moment will make the beam stretch on the upper side, so 290.5 kilonewton meters. And since when we integrate something, the line changes, so horizontal lines change to linear lines. So 290.5 minus 132 kilonewton meters is equal to 158.5 kilonewton meters. Now we have a bit of a complex structure which consists of one square and one triangle, and we'll add those areas together and which is, firstly we will do the square part, which is 23 times the base 3 plus the triangle area, which is 3, which is the base, times the height, which is 44 minus 23. And we divide that all by 2. And we will get that this is equal to 100.5 kilonewton meters. (158.5 minus 105 will give us 58 kilonewton meters. And since this line on the shear force diagram is a linear line, when we integrate a linear graph, it will turn into an exponential line. Now at this point we have this moment, this 12 kilonewton meter moment, which is acting clockwise. So 58 minus 12 kilonewton meters will give us 46. And finally we have our final area, which has the height of 23 and the base of 2, which will give us 46. And 46 minus 46 is equal to 0. Again, in the shear force diagram, this is a horizontal line, and when we integrate that, it will turn into a linear line. But yeah, that's it for this video. Finally, our final beam example will be an overhanging beam example, and then we'll move on to frames. If you